Hi, I'm Mike from MotoIQ, and today I'm going to be presenting a video on a subject that you've been asking about quite a bit. Now, you've probably seen our LS videos and how to build like kind of high dollar, kind of cool LSs, big power. And a lot of you have been asking, well, what can you do with a 5.3? We did do a video about how to do a refresh, super low buck on the 5.3, and that was really popular. But I think you guys want to know about the internals of a 5.3 and how you could build a pretty good 5.3. So a 5.3 is the most common LS variant. Like there's millions of them in junkyards. You can have one for as little as 200, but I would say between 200 and 600 is what your typical junkyard 5.3 is. The engine for this particular build was a $250 one that we just picked up, and it was kind of yucky and dirty looking, but it was plenty good enough to build this killer motor. And I think like one of the things we're going to be talking about is, everyone knows about LS3s and LS7s and the aluminum block variants. Those motors are really cool engines, but they're really expensive in junkyards. Like recently I did a look to try to find an LS3 used motor from a junkyard, and I couldn't find one for less than $5,000, and which got me to think, you could probably build a 5.3 and put 4 or 5,000 bucks of parts into it and have an engine that could whoop, an LS3 out of the box for about the same money. And the only disadvantage would be maybe it weighs about 50 pounds more, and that's about it. I really like the 5.3. It's a great motor. Even the cheap varieties are pretty robust and pretty good performing. Like before, it was the small block Chevy swap, but really the 5.3 smokes a small block Chevy. Look out! I just made fun of the most iconic engine ever made, but the 5.3 is a great engine. So we're going to be talking about extensively building one, but you don't have to do all this. Like the 5.3 is just pretty good out of the box. You can just get it from the junkyard, do a compression leak down check, just do a basic stock freshen up and throw it in whatever you're going to throw it in. And it'll still do a pretty good job. Like you don't have to get all this trick stuff. Like look at our freshening the LS3 video, and you can see what a low buck deal it could be and how you can do that and throw in your Jeep, throw it in your Nissan S chassis or whatever, and it's still a pretty nice performing engine for like incredibly cheap. There's different levels, so you can get your 5.3, let's say it's pretty solid, your bottom end's good, you can just throw a mild cam in, like we're talking about this hydraulic roller here. It's Comp Cam's drift specific hydraulic roller, but they also make a version of this cam that's a little milder that just drops straight in the bone stock engine. And that can give you 50 horsepower, and you can run the stock valve springs, stock lifters, and everything. So get your stock 5.3, drop one of these cams in, put some nice headers on, and away you go. You have a pretty powerful, fun little car that didn't hardly cost you anything. Another thing about the 5.3 is it's all cast iron. It's pretty strong. It's really good for forced induction, even when it's stock. Like you get a totally stock one, put on a drop-in like Vortec or like Eden blower, and you can make 500 horsepower with the stock bottom end as long as it was in pretty good shape and you have a nice tune that doesn't stress it out too much. So 500 horsepower, even 600 with a total stock bottom end is pretty great. And if you wanted to get a little bit more silly, I mean, you can do rods, pistons, mild cam and bearings, and good head gaskets and maybe some studs. Your 5.3 can make 1,000 horsepower with forced induction. Like, I don't think it'll do it for a super long time under hard conditions like drifting or something, but surely 800 horsepower with just pistons, rods, little cams, some studs, and some good bearings. To me, that's pretty amazing, and it's very little money. Now, I wouldn't like want to push beyond 800 horsepower for hard use. Like, it still only has 4 bolts per cylinder, and the head gasket's kind of a sticking point there. But with the stiff iron block, you could probably go 1,000 on a street car or one that you take to the strip every once in a while, and it'll be just fine. You can make big power with force induction or even nitrous for very little money, as long as you know your limitations, know your tuning, and don't go crazy. With that being said, what we have here is to build the 5.3 LS3 killer. It was done to, it's some money, but we figured it would be about the equivalent price of a used LS3 in the junkyard. And they'll be able to whoop it and probably make about at least 60 more horsepower. I think it's going to be more like 80 or 90 horsepower more than a stock LS3. So this is a naturally aspirated build, and it's really not that crazy. So don't be intimidated by the pile of parts on the table. There's nothing exotic like, mechanical Valvetrain and all that. And we tried not to get the most expensive parts. Now this engine is going to go into a drift car, and it's going to be a Pro-Am level drift car, so it has to have a lot of durability and be able to take quite a bit of abuse, even though it's sort of an economy engine. So it's a thorough build, built to be driven hard on the track, drifting. So that means banging on the rev limiter, clutch kicking, just going full bore all the time, and at full throttle for a minute. In my opinion, drifting is one of the most stressful things you can do to the engine. Off-road racing, power boats, and drifting is probably number 3. Then road racing. Street cars and drag racing is kind of way down there unless you're doing extreme drag racing. But this engine's going to be tough and built to take it. Like a lot of other people go, oh, your engines are way too complicated, and I make more horsepower for less with my eBay parts. Well, you know what? Take your stuff to the track and we'll see. I bet you it's not even running after one session. So with that being said, let's get into it. So we're starting off with our $250 Junkyard LS3. And the first thing we're going to do is getting some displacement out of it. So we're using Manley parts for the bottom end. And Manley is a really good bang for the buck brand. It's not like super esoteric. They have a good amount of shelf parts. And I really think for shelf parts, their parts are really feature rich. And they're at a really good price point. So let's start off with the crank. The crank is really important for durability. What we're doing here is we're increasing the stroke to 4 inches. To me, 4 inches is kind of a LS sweet spot. You get bigger stroke, you get kind of weird in the bottom end. The geometry's weird. It's better to go to a tall deck block and all the headaches associated with that. But a 4-inch stroke with a regular deck height LS is really doable. And I think it gives good results. Piston speed's reasonable. Your life is going to be reasonable. Bigger strokes go to higher piston speeds, more stress on the bottom end, and quicker life of the rings and stuff like that. So to me, 4 inches LS sweet spot. I guess another thing that people don't talk about much is if you stroke more than 4 inches with an LS, with a stock deck height block, you get a lot of rock around bottom dead center because the pistons kind of go past the skirt of the bore. So the skirts of the piston aren't too well supported. So the piston kind of does this rock. And if you see LSs that have been stroked with more than 4 inches with the stock deck height and stock or close to stock rod lengths, you always see this weird wave wear pattern on the bottom of the bore. Um, and you can actually see it in the measurements. And then you see a weird wear pattern on the piston skirts. And I think that is not too good for long-term durability. It's kind of evidence that there's a lot of stress going on and it's not good. So no matter what guys say, for a stock configuration block, I don't like to go more than 4 inches. So this is a Manley 4-inch stroke crank. Now it's fairly inexpensive, but it has a lot of features. First off, the material. It's forged from 4340. 4340 is a high nickel, high chromium steel alloy. You know, like everyone's heard of 4130 chrome moly, and you know that that's maybe twice as strong as regular steel or 50% stronger, to be more precise. Twice as strong was way off, but 50%. So think of this as 4130 with more nickel in there. Now nickel makes it even stronger than 4130 and it imparts toughness and impact resistance into the metal. And that's the exact kind of increase in strength you want to see in the crank because it has repeated cyclical pounding loads applied to it. So it's a really good material, 4340. You look at the crank pins are kind of hollowed out to where it's safe to do so to save reciprocating weight. The crank itself has generous fillets, way more than a stock crank. So a lot of the stress on the crank is right in this fillet area. And when you have a generous radius like this, it takes out a stress riser and actually improves the crank's fatigue strength quite a bit. So you're looking at this fillet. The counterweights are, like nicely shaped. They're not particularly bull-nosed, but, they are contoured to have some good aerodynamics and anti-windage characteristics. The crank comes micro-polished in the journals, and it's also been subjected to a severe shot peening. Shot peening forms a compressed skin over the part and really improves fatigue strength. You're probably looking at a 100% improvement in fatigue strength. Fatigue strength is the amount of cycles the part can take before failure, and it prevents cracks from propagating in the surface of the material and spreading to the inside. You also look at the oiling holes. They're teardropped and chamfered from the factory, so that's a thing you don't have to do. It's a really nice piece. It has a lot of the features of an expensive racing crank at a fraction of the cost. One thing that we're probably going to do is we're going to tack weld the reluctor onto the crank. Now we found in drifting, it's kind of common for LSs for the reluctor to slip on the crank and you lose your spark and start getting misfire and stuff. There's something about the way drift cars load up the crank that just makes the pressed on reluctor come off. Now I've seen almost all like higher level LSs without a welded in reluctor spin it. This is kind of like pro level, but it doesn't really cost anything to tack weld your reluctor on. So, put some TIG weld tacks on it and you'll never have that problem. I can't say enough about this crank. I can't believe what you get for the price. It's a really good unit and it's going to serve us well. I mean, this crank will hold more than 1,000 horsepower if you're going to do forced induction, and it's a nice shelf piece. The next thing is the rods, and we're using Manley rods again. This is a shelf rod. It's 6.125 in length, so it's longer than the stock LS rod. I like running a longer rod when I can because you get a better stroke to rod length ratio. This gives you a little bit more dwell time about top dead center, so you have more time to fill the cylinder. It helps volumetric efficiency. And on the power stroke, your piston, the explosion of fuel and air has a little bit more time to impinge on the top of the piston, so that improves your thermal efficiency. Also, there's less angularity in the rod while cylinder pressure is high, so it doesn't put so much bending stress on the rod and doesn't dig the piston into the cylinder walls as much. So there's less mechanical stress. So I try to, if I can get away with a longer rod, I like to do that. This is a mildly longer rod, and it's probably about the longest rod you can get with a 4-inch stroke with a shelf rod, shelf crank, and shelf pistons. I'm trying to stick with all shelf parts because they're cheaper, they're easy to get, and they're in stock. So nothing custom, nothing that's on back order, all stuff that any one of your Manley dealers probably has sitting there on the shelf. Now the Manley rod is a pretty budget piece, but there's nothing budget about its construction or quality. Like the crank, it's made out of 4340 steel, so an ideal alloy for repeated sharp impact kind of loads like a connecting rod's going to get. It's machined from a near net shaped forging, so it has good grain flow alignment for the beam and around the big end. This helps strength. Like when you talk about grain flow in metal, think about grain in wood. You know, like when you mess with wood, you could snap it across the grain real easy with your hands, but when you're with the grain, it's way stronger. It's the same thing with metal. So, you know, good grain flow, good grain alignment. We're running the optional ARP 2000 bolts. These rods come with a less expensive Manley bolt. There's nothing wrong with that. It has slightly less optimal properties than the ARP, but you know, it's a low price option, so I never cheap out on rod bolts because it's the most highly stressed part of the rod, and if you have a failure, you know, that's all over with. Like I said, there's nothing wrong with the stock Manley rods, but they do have that ARP option, and for myself, I always use it. Now, if you are not building a drift motor and not stressing it, or you don't have big nitrous or big forced induction, the Manley rod bolts are totally fine. The Manley rod bolts are actually probably fine for the other applications too, but a little bit of assurance, I'll pay a little bit more and get the ARP. You have a silicon bronze bushing on the small end. That's typical for race rods, but you know, it's nice with a floating pin. A feature I really like is the pin oiler holes are at the base of the bore here. There's two small holes in each side. Now typically you have one bigger hole on the top, but the very top of the rod is pretty highly stressed due to centrifugal loading. There's not a lot of material up there. I'll take two small holes down here if I can get it. I mean, there's a lot of really good high quality rods that have the hole up here. But I mean, shoot, if I can get it, I'd rather have the holes down here. The rods are also subjected to a severe shot peening, like the crank. The shot peening forms the compressed skin that makes it hard for cracks to propagate, increases the fatigue strength 100%. Now, we have the crank and rods cryogenically treated by CTP Cryogenics, and we also had them WPC treated afterwards. You know, we did videos on cryogenics and WPC, the processes. In short, they probably increase your parts life by about 100%, especially when used together. The cryogenic treatment on steel acts like an extension of the heat treating process. It kind of converts the steel from a body-centered cubic to a face-centered cubic structure, so it converts that austenite into martensite. It's just like heat treating, makes for a stronger part. Now, that's a bunch of science. I'm an engineer, so that's easy to understand for me because I had metallurgy, but I know you didn't. But let's just say it's not voodoo or weird stuff. It's actually metal treatment that works, and there's science behind it, and it really helps. If you're curious about this stuff, watch our last video that was on WPC and cryogenics improving engine life greatly, and give more details there, and it's probably pretty interesting for a lot of you. The next thing we're looking at is the piston. So this is a Manley shelf part. It's designed to work with a stock LS deck height with a 6125 rod and a 4-inch stroke. It's a flat top design. This is going to give about anywhere from 10.5 to 11 to 1 in your typical LS, which is, perfect for a kind of mild motor that has to run on pump gas, and maybe the gas quality might not be the best. So you can tune a 91 octane crappy California gas, you'll be fine. It'll also work better on race gas. So it's a reasonable compression ratio, kind of conservative. The piston is forged from 2618. That's a low silicon alloy. The advantage to 2618 is it's very ductile and very tough, so it can take a lot of abuse. There's other piston alloys like hypereutectic or 4032. They can run nice tight piston wall clearances, but they're brittle and more fragile. So for any engine that's going to see competition use or abuse, hard use, we go to 2618. The only disadvantage to 2618 is by its ductile nature, it is a little bit softer, so it doesn't wear as long as like a stock hypereutectic, and you get more wear in the ring grooves from the rings, more skirt wear. But we're not building a 300,000 mile engine. This engine could probably go 100,000 probably, but it can probably go 60 hours of competition use before refreshing, and that's quite a bit. The piston runs a modern ring package. It has a symmetrical skirt. It's a little short skirt for low friction, but the skirt's pretty wide for pretty good support. It's kind of a good compromise for the stroker engine. The top ring is a steel nitrided low tension ring, kind of narrow. Really good for life and taking some of that combustion heat. The number 2 compression ring is iron, and it's a Napier profile. This is designed to seat in real quick and get you good compression from the get-go. Napier profile kind of has a little hook on the bottom. It's really hard to see in the video, but that little hook thing on the bottom kind of beds in real fast and wears in and gives you immediate seal. The oil rings are thin, low friction, typical oil rings. And one of the unusual features is, since we're running a longer rod, the piston pinhole actually goes up into the oil ring. You can probably see that right there. Since it's into the oil ring hole, the oil ring needs a special support ring. Now this sits beneath the oil ring, and it spans this gap right here. See where it kind of goes into the oil ring? So that supports the oil ring over the gap, enables us to run the pin up into the piston and run the long rod with the stroke with the stock deck height. Piston pin is like high strength steel. It's kind of typical. It's medium wall thickness, so it'll hold boost and all that probably up to maybe 1,000 horsepower. Well, when you go more than that, you have to have a more boost specific piston design. We WPC treated the pistons and the rings for durability. We also did CTP Cryogenics proprietary aluminum cryo process on the pistons. Now, this is something special that CTP does on aluminum. I don't understand the metallurgy of it, and they don't want to tell me too much because I guess it's their secret. But it supposedly improves the mechanical properties of aluminum quite a bit. I understand what it does with ferrous metals, but non-ferrous, I don't know. But it works. I've used it on a number of aluminum blocks with really good results. I've done it on wheels. On wheels, it's interesting. Like it helps the resilience and makes the wheel stiffer, and it actually equates to faster lap times I've actually measured. So that's interesting. Um, like I said, it's secret. I don't even care to know. I just know it works, and that's what we did on the Pistons. For bearings, we use King XPC bearings. These are one of my favorite bearings to run on any engine. Um, it's a tri-metal, so you have your steel base, you have your lead and some alloy, probably tin or something, as your main substrate, and you have like an overlay on top that's a softer metal. So you have like a softer metal like zinc or something, which helps your embeddability, and then you have your harder like tin lead in the middle and your steel back. So the harder tin lead gives you more load bearing capacity. The thin surface that gives you embeddability. So that means like if there's like dirt or debris in your oil, like it won't get ground into your crank, but it'll kind of embed in the soft part of the bearing and kind of be rendered harmless. A unique thing about the XPC is they have a polymer coating on the top. Now most polymer coatings kind of work with the soft top layer and make it a little bit slipperier maybe. And they give it some forgivingness and more embeddability. But the XPC top layer is unique. It's a polymer, so it does all of that, but it also has copper nanoparticles in it, which also gives it the ability to bear load. So their top polymer coating actually improves the load bearing capacity. And I've used these in pretty severe applications like road racing and pro drift cars that make well over 1,000 horsepower. And sometimes we take the bearings out and they don't even look worn one bit. So that's a interesting thing about them, but that's why King's my favorite bearing. We're running a Moroso high volume, high pressure oil pump. Um, Now these iron blocks, this isn't as critical like the aluminum blocks, like a LS3. The aluminum expands and you tend to lose some of your hot oil pressure. Now these don't, but for an engine that's going to see competition, especially something like drifting or road racing, I always like to see a good amount of oil. Now, when you throw a high volume pump in the LS, you have to make sure you have sufficient clearance around your pickup. Like you would probably like to see like at least, a half inch or between the bottom of your pickup and the bottom of your pan. And you also want to have a high capacity oil pan because a lot of these LS pumps can drain the sump dry or make the level low so you suck air. Also, the suction, if the pickup is too close to the bottom of the pan, it can create a vacuum and you can get some cavitation in the pump. So just don't throw these suckers in there. Pay some thought. Make sure you have extra oil capacity and make sure you have enough clearance to the bottom of your pan. The next thing on the bottom end is our main caps. Now we're running the stock main caps. They're steel from the factory and really strong. They have 4 bolts and cross bolts. So this is like a pretty strong bulletproof bottom end, especially when you couple it with the iron block. Now we're using ARP studs. ARP studs are quite a bit stronger than the stock bolts, and they're made out of a stronger, like super alloy that's like chromoly and steroids basically. And they have machine bolts and washers. The washers are a ground hardened washer, and that helps you get more accurate torque and kind of spreads the load out around the nut head. When you're using ARP studs, you're tightening the everything to a higher torque. So always check your mains to see if you need to be a line board. With an iron block, you don't need to be a line board that often, but you should check. But if you have an aluminum block, those tend to tweak more when you put studs in. But always check to make sure that you don't need a line boring. The other thing is always use ARP assembly lube when getting your torque. Don't just use grease or oil. Make sure it's the ARP stuff, and it actually makes a pretty big difference in how accurate your torque is. Finally, for the bottom end, we're using a fluid damper. The fluid damper, to me, is an important part on a competition engine that's going to see a lot of abuse. And it's also helpful on the stroker engine, because stroker engines do tend to have more vibration. The reason I like the fluid damper so much is that it has an inertia ring inside, and it's unconstrained. It's unconstrained, and it floats around the silicone glue. Not glue, but it's like goo. It kind of looks like snot. And your typical balancer, has your hub, and then it has like a rubber that's bonded to the hub and bonded to the inertia ring that lets the inertia ring move around. But it's constrained by the rubber. These OEM dampers are more tuned to a certain vibrational frequency, and they're kind of limited to attenuating vibration in that frequency. I think the big problem in the competition engine, instead of these vibrations, is more like torsional whip in the crank. There's a lot of things going on. The pistons are pounding on the crank. When you do a clutch kick, you're letting the engine rev and then catch. When the tires are spinning and catch grip, that all puts a lot of stress. The crank starts whipping, and that whip is what actually wears and damages parts and stresses everything in the whole engine, actually. So, with your unconstrained ring floating in silicone goo, the harder the crank whips, the harder this thing works, and the more it damps. So I guess your OEM damper is frequency dependent, but the fluid damper is amplitude dependent. So the more going on, the harder it's being worked, the harder this thing works to damp out some of that stress. There's other good dampers on the market, but in my opinion, when it's available, I prefer to use this over the elastomer style. So drift cars are really hard on their Valvetrain. They bang off the rev limiter all the time, which is really hard. That initiates valve float and losing control of the Valvetrain, bending valves, wrecking rockers. In the case of the LS, even cracking the intake port. Comp Cams has developed a drift-specific pair of cams that are really good. They're designed to reduce stress on the Valvetrain and reduce the likelihood of valve float. Like they have kind of gentle acceleration ramps, but they're really good at that magic. And even though the ramps maybe aren't that aggressive, these suckers still make a lot of power. Like Comp has dropped this particular cam into a bone stock 5.3 and gotten 70 or 80 horsepower just on the cam. I forget the exact numbers, but it's something amazing like that. So this cam is the biggest of the two drift-specific cams. So you have to run their valve springs with it, but they also make one that just drops right into your stock engine. It's a little bit milder. But we're going to spend a little extra money because this is actually going to be a Pro-Am car and seeing competition. So we got the bigger cam. We got the valve springs. We're running their anti-pump-up roller hydraulic lifters. These have less lash take-up than a stock lifter. So that means at high RPM, there's not as much to pump up to cause valve float. They also have this bar linkage. The bar linkage keeps the lifters from turn sideways and skidding. So your stock LS has lifters with flats machined in it, and the flats sit in this plastic tray that sits in the valley of the engine that has holes to accommodate those slots. And the plastic tray is what keeps the lifter from spinning and skidding. However, that sucker wears out, and then pretty soon you start getting play. Plus, it's plastic, so if anything happens, like the lifter could just bust through the plastic and skid sideways. Now, we've seen that happen quite a bit. And most of the time, the engine still runs kind of okay, but it's, the skidding sideways lifter is gouging everything up and making a mess. And pretty soon, something bad, really bad is going to happen. So the bar linkage positively prevents that from happening. You can kind of see it lets everything go up and down, but totally prevents it from turning. Another problem the LS has is the rocker arms can skid sideways when you valve float, hit the limiter, clutch kick, and all that. So normally what we've been doing is running really expensive shaft rockers from Jezel or something. The shaft rockers, instead of being on the trunnion, the rockers pivot on the shaft. And the high buck ones have roller bearings and a roller tip. And they're made out of, like a high grade aluminum or stainless. And they're pretty high dollar. I mean, just the shaft rockers cost a couple $1,000s at least. But Comp Cams has come to the rescue with their BRS shaft rockers. Now, these are an investment cast rocker, and they pivot on bushings, and they're on a shaft. So unlike the trunnion, there's no way this thing can pivot and skid sideways. It's being held positive, so even if the valves float, it's not going to skip out on you and skid sideways and cause you to drop a valve and blow up. These things are really inexpensive. They're like probably less than a quarter of the cost of some fancy full race shaft rockers. They're tough too. Like on the Sorensen Motorsports cars, they use these, and they've held up with no problems at all for season after season on a 1,400 horsepower Pro Drift car. In fact, Sorensen's use this whole Valvetrain from Comp Cams. So this reasonably priced thing works on everything from a Pro-Am car to your street car to like a pro drift car, depending on the application. This is an incredible bang for the buck. I mean, I would run these on the street car all day. The other thing that happens is when bad things are going on with the Valvetrain, LSs can sometimes crack the head from the rocker pedestal to the intake port. I've seen this happen a bunch on like pro cars. So when you have a shaft rocker system like this, the load is spread over the whole shaft, so like you don't have all the stress going into one intake port. And I've never seen an intake port crack with shaft rockers. So these things are cheap insurance. Run them on your street car, run them on your race car. This is a great innovation from Comp, and competition proven even. Finally, Comp Cams makes this double row timing chain for the LS. The timing chain has always been a weak point on LSs. They come with a single row, and until fairly recently, nobody's stepped up to do a double row chain, but Comp has one. So, there's 2 rows. It's twice as strong as the stock chain. What I like about the Comp Cam is it has a billet main gear. It has a roller thrust bearing instead of just a plain sheet thrust bearing. So there's no way that thrust loads are going to cause any damage or create any extra friction. Also, the cam timing is adjustable. This is like really important for dialing in your cam. It gets ignored a lot, but on the single cam engine, like if you align bore the engine, you're shortening the distance between the cam center line and the crank center line, and your cam timing gets more retarded. So you can restore it with this and also degree in your cam. Like a lot of cams like to be installed slightly advanced, and this lets you do it. Like a lot of backyard builders just slap her together and don't degree in the cam, and that's one of the reasons why backyard motors don't run that hard, because cam timing does make a big difference. For head gaskets, we're going to be trying a new gasket from SCE. I haven't had any experience with these, but they look really promising. They have a sealing ring, a metal one, that goes around the bores, and this gives a really positive seal like an O-ring, but they have a composite body that gives the forgiveness and the positive sealing around the water jackets. So you have the strong, higher metal, and you got the composite. Now these gaskets are supposed to be really good with boost and nitrous, high compression, and you get the sealing of an O-ring type gasket without having to cut a receiver groove in the block. They just drop right on. You put the composite part on first, set the metal sealing ring in there, and put the head on top of it. So you get the best of both worlds. Now, like a lot of people talk about copper head gaskets. I haven't had a lot of personal good luck. Copper is really good at sealing combustion, but really bad at sealing water. So no matter what kind of stuff and how I treat a copper gasket, those engines always seem to consume a little water. This may or may not be a problem. You know, if it's a race motor, a little bit of weeping might be okay to you. I don't like it myself. If you have a performance street car, you probably don't want your garage to stink like coolant and see a little green film around your head. You know, so I don't like that. I usually try to do everything I can to avoid copper head gaskets. So this gives you the best of both worlds, hopefully. Metal sealing ring, seal that combustion pressure, and the composite and polymer to positively seal the water jackets. The manufacturer tells me that this is the bee's knees, so we're going to find out. Now, the whole thing about that circles around this engine that's going to help it make big power are these particular Edelbrock cylinder heads. You know, they're kind of an expensive addition to this project, but I think they're well worth it. The 5.3 comes from the factory with a cathedral intake port. This is a long, skinny port that kind of has like a peak at the top, so it kind of looks like a church roof, so they call it a cathedral port. Now these are kind of the original ports that the LS came with, and they flow better than the small block Chevy by quite a bit, but it's nothing like the square port heads like the LS3 and LS7 have. So the later heads flow quite a bit and they make quite a bit more power. The disadvantage to the later heads is that they don't work on the 5.3 because of the small bore. Now the 5.3 can be bored out to 3.9 inches and still have a little bit more, so you can maybe rebuild it one more time. So ours is 3.9, but if you try to slap LS3 heads on there, the intake valve goes right into the cylinder wall, and so that's no good. So what Edelbrock has done is they kind of morph the 5.3 head and the LS3 head to make this head that has the valve spacing so you can run the smaller bore engines, but it has the big LS3 rectangular style port. Now this head is worth at least 50 horsepower over the cathedral ports. The intake port flows about 26% or even more than your typical 5.3 cathedral port, and the exhaust flows a whopping about 30% or more over your typical cathedral port. This head also has really nice combustion chamber geometry. It has like a nice tight combustion chamber. It has like a lot of quench away from the spark plug. Now this quench, as the piston comes to TDC, It squishes all the dead fuel air mixture from the hard to ignite corners of the combustion chamber and pushes it toward the spark plug, so you get a better burn. The nice shallow chamber, when combined with the flat top, gives you a real nice flame front. So these chambers are real efficient. It's a fully machined combustion chamber, so your CCs are going to be perfectly the same on all your cylinders. And as you can see, there's generous radiuses, all the way up to the maximum bore size here, so you get maximum valve unshrouding. The radius goes all the way to the bottom by the valve, so there's a lot of area for the valves to flow at low lift. These heads are kind of as cast, but they're kind of hand finished, so the seats are matched, and they're the ports are pretty good. You don't need to do anything extra. You can bolt these right on, and like I said, at least 50 more horsepower. The heads aren't that much, and you can use these heads and still be about matching the price of a used LS3. Now, if you wanted to build a more budget engine and not spring for these heads, I mean, you can do everything here on the table or even less, but some cathedral heads are better than others. So they have the 243. I'm going to talk about casting numbers. So the 243, 799, 364, and 317 heads are all your better 5.3 heads. They all have bigger valves, and the ports all flow better. The 317 head has a big chamber, so that's good. Let's say you're building a forced induction motor and you want to lower the compression ratio. These heads could probably be found for a couple $100 at the junkyard, or you get an engine with these heads. To spot them, on the corners of the heads, there's a little tab cast into the head, and the numbers stamped in there, so that's how you can tell what head you're getting. So these are some of the common cathedral port junkyard heads that work better. The combustion chambers, CCs, are a little bit different than all of them, so measure your chamber CCs and plan accordingly when you're selecting your pistons, so that way you know what compression ratio you're getting. Edelbrock has two variations of this head. There's the 61-329, which bolts on your typical 5.3. There's also the 61-319, which has this extra boss here. This extra boss is if you're running an LSX style block, so you have the extra bolt that those blocks have. So that's the LSX GM aftermarket block. A lot of aftermarket blocks also have this boss, and LS7s do. Now, you're probably not going to run an engine that needs this. We're probably just going to cut this off, and it'll work on the regular old 5.3 there just fine. But that's the thing to note about the two different part numbers. My opinion, this head is going to revolutionize the 5.3 market and make the 5.3 on par with the more expensive LS variants. So we have all these cool parts back there, but we got to put it in something. So we have our 5.3 block here. This is a pretty sad, crusty, grimy, rusty sucker. We cleaned it up, machined it, and now it's good to go in our engine. What we did is we bored it out to 3.9 inches. So with our stroker crank, that gives us about a 383 cubic inch motor, or it's close to a 6.3 when it comes to liters. So we're going from a 5.3 to a 6.3, so that's a pretty huge jump in displacement. We can go a little bit more. We could probably go 395, or maybe even a little bit more than that. So we have one step to go in case we need to rebuild it. But these blocks are so cheap, it almost doesn't matter. We did some kind of high-end things that you don't really need to do, but it's nice. We're building this sucker to last, and to go a long time in between refreshes. So before we did anything, we hot tanked the block to get the years of grime and crud off of it. Then we took it to CTP cryogenics to have it cryogenically treated like the rest of the motor. In my opinion, it's best to do this before you do any machining, because during the stress relieving and process, the block can shift around. You're changing the metal structure, so you can have some dimensional changes. So we wanted to do it before we did any machining. So after cryogenic treating, we bored it out. We used the torque plate. If you're just doing a casual refresh with these iron blocks, you don't really need to use a torque plate, but we're boring this block a lot, which puts more stress into it. And we're also running studs. Studs are tied into a higher torque, so they tweak everything a little bit more. So we opted to go to a torque plate. In my opinion, a torque plate is more important than aluminum blocks. They tend to tweak more. Usually these cast iron blocks are pretty solid, but with our studs and the big skip and bore sides, we use the torque plate. So we bored it. We did a final hone with like a 480 per what lake speed says, and then we did a plateau hone. The plateau hone is kind of like a fine hone that knocks the peaks off your hone surface. So, when you do a coarser hone, the surface is kind of jagged like that. And the jaggedness, causes more wear, more friction, tears up the rings more when you're breaking in. When you break in the engine, those peaks get worn down and everything gets nice and smooth. But what the plateau hone does is it takes the tip off the peaks, so it almost kind of does a pre-break-in, but you still have the valleys that hold lubricant for the cylinder walls. So you kind of get the best of both worlds. As you can see, the plateau honing leaves a nice, smooth finish. After we did our main machining, we took it and we got the bores WPC treated. That kind of gives them a little bit of surface hardness and kind of puts dimpling on top of the hone pattern, which also helps retain lubrication. And it also kind of makes things smoother and lustrous, and it greatly reduces friction and improves the life of the cylinder walls. Now that's a real deal. Like if you looked at our last video, we could show the almost negligible amount of wear, and time again I've measured blocks that have been WPC'd, and the wear is about half of what you would expect always. The smooth surface also reduces friction, probably frees up power. Common sense would tell you it gives you more power, and when you spin the engine when you're assembling it, the engine spins around a lot easier. How much exact power it gives, I don't know. Never did an A to B test. That's kind of a hassle and expensive. But, you can feel when you're just spinning the engine by hand that there's a lot less friction. So that would tell you probably frees up some power. This engine has all of our tricks. Like I said, the 5.3 is basically a budget kind of engine. You don't need to do all this stuff, but we're doing it because it's actually going to see hard use and competition. So why not? It's, my opinion, money well spent. It saves money because you can increase the time between refreshes. So, your power stays more consistent over the life of the engine, and probably helps your reliability too. So in this kind of use, it's money well spent. If you're on a budget and you're just trying to get the cheapest engine that can see you through, I'd say, you don't really need it, but it's good to have. So all this stuff naturally aspirated. I think this engine's going to make somewhere around 530 wheel horsepower, give or take some horsepower. I haven't actually used these heads yet. They're really new, but I think the power is going to be there. If you wanted to use the cathedral port heads, if you get some of the better ones, you'll probably be looking at high 400s, like maybe 470, 480. Like Some of the cheaper, like really cheap cathedral ports, maybe 440, but that's still nothing to sneeze at, and a very cheap motor. So I hope I answered most of your questions about how to build a 5.3. I think I talked about how much I like this engine, and I think it's going to be the next hot swap small block Chevy for many years to come. Like I said, there's tons of them in junkyards. They're currently very cheap, and man, you can do a lot. So if you like this content, be sure to subscribe. We're going to have a part 2 to this video about some of the outside parts to build the Killer 5.3. Also, you can probably enjoy some of our other technical content. If you want to support our channel, we have an online store. Buy your parts there, and that helps us out. Also, you can become a MotoIQ member. So there's a little thing you can click. As a member, you get to see some of the content earlier, and we'll be working on some exclusive content, but mostly think of it as a way of saying thank you and helping us out. Our next video is going to be part 2 on the peripherals of this motor, and we're going to have a part 3 about the parts we need to get it to fit into our S13. So keep on watching, and we'll keep on making stuff.